Hello and good afternoon. First and foremost, I would like to introduce myself and my fellow teammates. I am Tan Su-Sien, and my friends here are Mukesh, Singh, and AMIZATUL BALKHIS. All of us are from program RK20, and today we are going to present you the results of the mini project given to us, which is missile control system. As you can see, a high-performance missile control systems needs a sophisticated control mechanisms. So in order to achieve that, we were given a model of missile systems with a compensated network GS. In the network, we have to find the phase and gain margin of the process, which is 40 over S times S plus 5 times with S plus 2. And as for the GS, it is the compensator of the systems. We have to find and determine whether a lead and lag compensator is suitable for the systems to achieve a stability throughout the whole time. Aside from the conventional method of plotting the BODE plot in a semi-log graph, we are going to use the Scilab. In the Scilab console, we can start with S equal to %S. This is to show that the S representing a polynomial form. Then we will declare num equal to 40, which is the numerator. For then is equal to denominator is equal to S times S plus 5 times with S plus 2. Then we will declare the transfer functions. TF equal to syslin, bracket exclostrophy, C exclostrophy, comma, num, comma, then. The syslins is to show that the systems is in a linear form. For the exclostrophy C, this is to make sure that the systems or the BODE plot showed will be in a continuous time domain. Then lastly, we will type show underscore margins bracket TF. This is in order to generate the magnitude and the phase plot of the systems. As you can see, these are the generated magnitude and the phase plots. The blue dotted lines are representing the phase margin, while the red dotted lines representing the gain crossover frequency of the system. In order to get a better and clearer value of the phase margin and the gain crossover frequency, we can type open bracket PM space GCF close bracket to show the phase margin and the crossover frequency of the gain equal to P underscore margin open bracket transfer functions and close brackets. After that, the value of the gain crossover frequency and the phase margin can be shown in the console, which is the GCF is 0.3736751, and for the PM it is 15.272026. And here we know that those are the values which are found in the phase and the magnitude plot of the systems.
This is the transfer function of missile control system. The transfer function given is GCS equals to 40 over S times S plus 5 times S plus 2. From the transfer function given, we have to simplify it until it becomes 4 over S times S over 5 plus 1 times S over 2 plus 1. From the transfer function, there is one pole at origin, two poles at P1 equals to 5 and P2 equals to 2. The value of K is equal to 4. The gain margin for this transfer function is 20 log 10 GCS equals to 20 log 10 4 minus 20 log 10 S minus 20 log 10 S over 5 plus 1 minus 20 log 10 S over 2 plus 1. The phase margin for this transfer function is angle of GCS equals to angle of 4 minus angle of S minus angle of S over 5 plus 1 minus angle of S over 2 plus 1. from the Scilab simulation, the gain crossover frequency GCF is equal to 0.3736751 degree, and the phase margin PM equals to 15.272026 degree. To find the GCF in omega m, we need to times GCF times 2 pi is 0.3736751 degree times with 2 pi equals to 2.347 radian in omega m. Additional phase margin is 30 degree minus 15.272026 degree equals to 14.73 degree. To find the phi max, 14.73 degree plus 15 degree equals to 29.73 degree. The phi max equals to sine negative 1 alpha minus 1 over alpha plus 1 equals to 29.73 degrees.
Okay, hi, my name is Mukesh, metric number 171020923. So I would be covering the calculation part for the compensator design. As you can see, we have chosen to design the lead compensator. So basically, to perform the calculation, there will be 5 steps we need to take note of. The first step is we want to find the system phase margin and the gain crossover frequency. And the second step, we want to find the phi max, which is required, addition for phase margin, and add safety margin. And the third, we have to solve for the alpha. The fourth, we use the alpha value to find the omega m and also the tau. And in the end, the fifth step, we want to rewrite the lead network transfer function in this form, which is GCS equals to 1 plus alpha tau s over 1 plus tau s. Alright, now let's get back to the first step. So the first step, from the BODE plot, we have found the gain crossover frequency and also the phase margin. The gain crossover frequency is about 0.3736751 degrees, while the phase margin is 15.272026 degrees. Okay, now what we have to do is we have to convert this gain crossover frequency into radian, which is by multiplying it with 2 pi, and we will get about 2.347 rad. And this value is actually the omega m. Right after this, we need to find the additional phase margin with and also adding the safety margin. So for the additional phase margin, we take 30 degrees minus with 15.27 degrees, and we will get about 14.73 degrees. And from there, that 14.73 degrees will be added with the safety margin, 15 degrees, and we will obtain about 29.73 degrees. And then the formula for phi max is for lead compensator, phi max is equal to inverse sin alpha minus 1 over alpha plus 1 equals to the phi max which we calculated before, which is 29.73 degrees. Alright, with the value of phi max, now we can solve for the alpha value. So what you have to do is, we place back the equation which we got just now, which was inverse sin alpha minus 1 over alpha plus 1 equals 29.73, and then now we solve for alpha. So first thing is, while we move the sin to the right hand side by inverse sine, move to the right hand side, so it will become sine 29.73, which will get 0.496, I'm sorry. And then we multiply the 0.596 with the denominator of alpha plus 1, and we expand up the equation until we get the alpha value, which is about 2.968, as you can see in the picture. Now we have two values already. We have the alpha value and also we have the omega m value. So right now, what we want to find is, we want to find the tau. So to find the tau, we write back the omega m formula, which is omega m equals to 1 over tau square root alpha. 1 over tau multiplied with square root alpha. So we substitute the values of omega m and alpha, which are 2.347 for omega m and 2.968 for alpha, and then we solve for tau, which we will get about 0.247. After getting these three values, which are omega m, alpha, tau, we only need the alpha and the tau value to be substituted into the lead network transfer function. So JCS is equal to for the lead compensator, the formula is 1 plus alpha tau s over 1 plus tau s. So what we do is we substitute the values which we obtained just now for the alpha value and the tau value, and we will get a final answer about 1 plus 0.733s for the numerator and over 1 plus 0.247s for the denominator. So that's pretty much it for the calculation part. Thank you.
Hi everyone, today I'm going to cover the simulation part in using Scilab. First of all, my name is Lin Xiang. My metric number is 171020903. Okay, now into the coding part. At first, we declare the S, and for the new numerator is equal to 1 plus 0.733 times S. For the new denominator is equal to 1 plus 0.247 times S. Then we declare the old numerator is equal to 3. After that, for the old denominator is equal to S times bracket S plus 5 bracket times S plus 2. After that, we declare transfer function is equal to the new numerator over the new denominator times the old numerator over the old denominator. Then we declare the transfer function is linear continuous transfer function. So in the coding is transfer function equals system linear bracket C comma transfer function. Then to combine the PM and the GCF is equal to P underscore margin bracket transfer function. And therefore the GCF is equal to 0.4519662 and the phase margin is equal to 34.854585. As you can see, the PM, the phase margin is more than 30 degree. And in the graph, we can see the new GCF and the new PM is leading the old GCF and the old PM. And also based on the new block plot, we can conclude that this system we are using is lead compensator. Thank you.